Good morning, students. Welcome to today's physics class. In the last class, we started the second chapter, current electricity. What do you mean by current electricity? It is the study of flow of electric charges. Define current. Current is defined as the rate of flow of charges through a given cross-sectional area. So I equal to Q by T. What is the unit of current? Ampere. It is a scalar quantity. Then we have discussed about drift velocity and mobility. What do you mean by drift velocity? The average velocity acquired by the electrons inside the conductor when it is subjected to an electric field. The unit of drift velocity is meter per second. Mobility is defined as the drift velocity acquired per unit electric field. It is denoted by mu and the unit is meter square whole power minus 1 second power minus 1. At last we have learned microscopic model of Ohm's law. So in the microscopic model of Ohm's law, we got the expression I is equal to NAE VD. This is actually the microscopic model of current. N is the number of electrons per unit volume, A is the area of cross section, E is the charge of an electron, VD is the drift velocity. From this, we have learned another one concept, current density. Current density J can be written as current per area, that is J is equal to NEVD. When we are substituting the value of VD, J can be as minus NE square E tau by M. So NE square tau by M can be as sigma minus sigma into E. Current density is a vector quantity. When we consider the current density and the electric field on the same direction, we can write J is equal to sigma into E, where sigma is known as the conductivity of the material. So J is equal to sigma, E is known as the microscopic form of Ohm's law. Microscopic form of Ohm's law. Today we are going to learn macroscopic form of Ohm's law. Macroscopic form of Ohm's law. So this macroscopic form of Ohm's law can be derived from the microscopic form of Ohm's law. Okay? Consider a conductor. Of length L. Area of cross section A. It is connected to a battery. The voltage V. So when there is no electric field, there will be no current. When the electric field is applied, the electrons will be drifted towards one side with the drift velocity V. Hence current produced. Now consider the electric field of the conductor is uniform for this entire length. Electric field is uniform. Then we can write the expression potential V is equal to E into L. How this expression comes? In the first chapter, you have learned potential is the electric field is the negative gradient of potential minus dV by dx. So from this, dV is equal to minus E into dx. So simply we can write V is equal to E into x or E into dx. So this formula we are using here. So potential difference or voltage is equal to E into L. Now, what is the microscopic form of Ohm's law? J is equal to sigma into E. J J is equal to sigma into E. So substitute the value of E from this equation 1. What is that? J is equal to sigma into V by L. Already we know the general definition current density, that is J. J is equal to I by A. So compare the equations 2 and 3. We can write I by A is equal to sigma into V by L. Now we can rewrite this equation as I is equal to sigma V A by L, or we can write V is equal to I into L divided by sigma into A. This term I sigma L sigma A, actually this term is constant. L is the length of the conductor what we are taking. Sigma is the conductivity, that is for a particular material, and A is area of cross section. So we can rewrite this equation as I into R. This is known as the macroscopic form of Ohm's law. So V is equal to IR, where R is known as the resistance of the material. R is known as the resistance of the material. What do you mean by resistance? It opposes the flow of current. It opposes the flow of current. The unit of resistance is Ohm. Unit of resistance is Ohm. So the resistance is directly proportional to the resistance can be written as L by sigma A. So resistance depends on, or it is directly proportional to the length of the conductor and inversely proportional to the area of cross section. So what is macroscopic form of Ohm's law? V is equal to IR. At constant temperature, the steady current flowing through the conductor is directly proportional to the potential difference developed between the ends of the conductor. Is I proportional to V. This is known as Ohm's law. Ohm's law states that at constant temperature, steady current flowing through the conductor is directly proportional to the potential difference between the two ends of the conductor. So J is equal to sigma E is known as the microscopic form of Ohm's law. V is equal to IR is known as the macroscopic form of Ohm's law. J is current density, sigma is conductivity, E is electric field. V is voltage, I is current, R is resistance. V equal to IR. Here the resistance R can be written as R is equal to V by I. So resistance is defined as the ratio of potential difference across the conductor to the current produced in the conductor. Resistance is directly proportional to the length and inversely proportional to the area of cross section, as well as resistance can be defined as the ratio of voltage to the current. What is the unit of resistance? Ohm. When we analyze the characteristics of voltage and current for substances, we will get a graph like this. The voltage is taken along x-axis and the current is taken along y-axis. For metals and the conductors, we will get a straight line. So when we get a straight line, we can say these materials obey Ohm's law. These materials obey Ohm's law. It is said to be in ohmic region. If we take the slope of this graph, slope means this is A, B, C. So slope can be as AB by BC. AB is nothing but I. BC is nothing but B. So we can write I by B or we can write 1 by R. So the reciprocal of the slope gives the resistance. And also some of the materials we will get a graph, not a straight line like this. This material does not obey Ohm's law. It is non-ohmic region. This ohmic region, this is non-ohmic region or non-linear graph. So here the materials does not obey Ohm's law. Here the materials are obey Ohm's law. So far we have seen J is equal to sigma E, V is equal to IR, then R is equal to L by sigma A, and R is equal to V by I. So J current density, V voltage applied, R resistance. Now we are going to learn resistivity. Resistivity. So R is equal to L by sigma A. Here sigma is known as conductivity. The reciprocal of this conductivity is called as resistivity. Resistivity is denoted by the symbol rho. It can be done as 1 by sigma. The reciprocal of the conductivity is known as resistivity. So we can rewrite the resistance equation. R is equal to rho into L by A. Rho into L by A. Where rho is the resistivity, L is the length, A is the area of cross section. R equal to rho when L equal to 1 meter, A is equal to 1 meter square. So we can define the electrical resistivity. Electrical resistivity is defined as the resistance offered to the current flow in unit length in unit area of cross section. The electrical resistivity of a material is defined as the resistance offered to the current flow by a conductor in unit length of unit area of cross section. What is the unit of resistivity? Unit of resistivity is ohm meter. Unit of resistivity is ohm meter. Because L by A, so we can write R is equal to rho into L by A. So rho is equal to R into A by L. So resistance unit is ohm. Area unit is meter square, unit of length is meter. So meter get cancelled, we will be getting ohm meter. So R is resistance, rho is resistivity, and sigma is conductivity. Okay? The sigma conductivity, rho resistivity. Based on this resistivity, materials are classified as conductors, insulators and semiconductors. Conductors, insulators and semiconductors. Conductors have low resistivity, insulators have high resistivity, semiconductors has resistivity in between conductors and insulators. Conductors have low resistivity, insulators have high resistivity. Conductors will conduct, insulators will not conduct. So it has high resistivity. The semiconductor has resistivity greater than this conductor and lesser than this insulator, in between the conductors and the insulators. So this is about resistivity. This resistivity is constant for a particular material and the conductivity depends on the type of the material. Okay, I hope you understood current, resistance, resistivity and conductivity. Resistivity for various material is given in your book. For example, for glass it is 10 power 10 to 10 power 14. For silicon it is 640. For aluminum it is 2.7 in 10 power minus 8. For silver 1.6 in 10 power minus 8 ohm meter at 20 degrees Celsius. So go through the book. Our human body has large amount of water as well as some resistance. Resistance of the order of 200 ohm. 200 ohm. The dry skin has the resistance 500 kilo. 500 kilo. But the wet skin has the resistance of 1000 ohm. Dry skin has the resistance of 500 kilo ohm. Wet skin has the resistance of 1000. So wet skin, the resistance is reduced. Dry skin, the resistance is high. So when the resistance is reduced, the conductivity is high. The current will flow very easy. This is the reason with a wet hand, when we are handling the electrical appliances, it is dangerous. This is the reason with the wet hands, when we are handling the electrical appliances, it is very dangerous. The next one is resistance, series and parallel. Resistance in series and resistance in parallel. Already capacitors in series and parallel we have learned in the first chapter. So what is the circuit symbol of resistance? This is the circuit symbol of resistance. When the resistors are connected in series, what is the effective resistance? We are going to learn. So consider three resistors having the resistance value R1, R2, R3 connected series. Series means one after the other. So let us see. This is R1 connected in series with the next resistance R2, and it is connected in series with next resistance R3. It is connected by means of a battery. So this is a series connection. Three resistors connected in series. When the voltage is applied, the current is flowing along this direction. Here, the charge on the series connection remains same. Across this resistor, across this resistor, across this resistor, the charge remains same. But because of the different resistors value, the voltage developed is different. So voltage developed between this and this V1, between this and this V2, between this and this V3. So what is the total voltage? Voltage can be as V is equal to V1 plus V2 plus V3. But the current value is same because it is a series connection. What is the value of V1? According to Ohm's law, we can write V is equal to IR. So V1 is equal to IR1. V2 is equal to IR2. V3 is equal to IR3. When you are substituting here, V is equal to IR1 plus IR2 plus IR3. So what is the simplified form of the circuit? The equivalent circuit is this is S, series combination resistance. So we can write V is equal to I into Rs. V is equal to I into Rs. So IRs is equal to IR1 plus IR2 plus IR3. We are taking I as common outside, R1 plus R2 plus R3. So I get cancelled. Then Rs is equal to what? R1 plus R2 plus R3. So when the resistors are connected in series, the equivalent resistance is equal to the sum of the individual resistances. So when we connect the resistance in series, the equivalent value will be greater than the individual resistances. I hope you understood this. Three resistors are connected in series, R1, R2, R3. The battery is connected, current is flowing across the series combination, current is same. Because of the various resistor value, the voltage developed is different. So V equal to V1 plus V2 plus V3, and we can write V is equal to IR plus IR2 plus IR3 according to Ohm's law. Then RS is equal to R1 plus R2 plus R3. The next one, resistance connected in parallel. Resistance connected in parallel. So parallel combination. Consider the resistance, 3 resistor. Connected parallel to a battery. So this has the resistance R1, R2, R3. This is the parallel connection. This sides are connected commonly to this positive terminal and this ends are connected commonly to the negative terminal. Since the voltage is connected parallelly, the voltage drop across each resistor is same. Voltage drop across each resistor is same. V same. But the current is splitted into I1 through R1, I2 through R2 and I3 through R3. So current is splitted. So according to the conservation of charges, we can write the current is equal to I1 plus I2 plus I3. Total current I is equal to I1 plus I2 plus I3. From Ohm's law, I can written as V by R. V is equal to IR, so I is equal to V by R. So how can we write I1? I1 is equal to V by R1, I2 is equal to V by R2 and I3 is equal to V by R3. Substitute here, I is equal to V by R1 plus V by R2 plus V by R. So this is simplified as a single circuit, that is the parallel effective circuit or equivalent circuit. So we can write V I is equal to V by RP. So V by RP is equal to V by R1, or else V we can take it as outside 1 by R1 plus 1 by R2 plus 1 by R. So V get cancelled. 1 by RP is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So when the resistors are connected in parallel, the reciprocal of the equivalent resistance is equal to the sum of the reciprocal of the individual resistances. The reciprocal of the equivalent resistors when the resistors are connected in parallel equal to the sum of the reciprocal of the individual resistances. So whether the equivalent resistance is high or low, the equivalent resistance will be low than the individual resistances. So when it is connected series, the equivalent resistance is high. When the resistors are connected parallel, the equivalent resistance is low. But just opposite that of capacitor. In capacitor, while connecting series, we will get 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. And parallel, CP equal to C1 plus C2 plus C3. But here, resistance in series, RS is equal to R1 plus R2 plus R3, and in parallel, 1 by R2 is equal to 1 by R2 plus 1 by R1 plus 1 by R2 plus 1 by R3. Household appliances always connected in parallel, so that if one is switched off, the other devices functions properly. Okay. So far we have seen the resistance, series and parallel. Let's see the problem related to this topic. Example 2.9. Calculate the equivalent resistance in the following circuit and also find the current I1 and I2 in the given circuit. Calculate the equivalent resistance in the following circuit and also find the current I1 and I2 in the given circuit. So this is the given circuit. 4 ohm, R1 equal to 4 ohm, R2 is equal to 6 ohm. The voltage is given as 24. They are asked to calculate the equivalent resistance. Equivalent resistance and also I1 and I2. Look at this circuit diagram. Here the two resistors are connected in parallel. So what is the effective resistance? 1 by Rp. 1 by Rp is equal to 1 by R1 plus 1 by R2. We are asked to calculate what is the equivalent resistance. So 1 by Rp is equal to, what is 1 by R1? 1 by 4 plus what is 1 by R2? 1 by 6. So answer is 5 by 12. This is 1 by Rp. While doing problem, we have to take the Rp value. So Rp is equal to what? 12 by 5 ohm. Now I1 and I2 we are going to calculate. Since the connections are parallel, the voltage remains same. Voltage remains same. So we have to calculate the value of I1 and I2. And also I. What is the formula for I1? I1 is equal to V by R1. I2 is equal to V by R2. So V by R1 means what is V? 24 divided by what is R? 4. So what is the answer? 6 ampere. Next, I2 is equal to V by R2. So what is V? 24. R2 is 6. So what is the current? 4 ampere. So equivalent resistance we have calculated, and I1 and I2 also we have calculated. Find the current I we have to calculate. So what is the value of I? I is equal to I1 plus I2, that is 6 plus 4, that is equal to 10 ampere. So like this, some problems are solved in your book. Go through the problems and practice it in the notebook. Okay. So in this chapter, you have to complete the questions. What is why current is scalar? Distinguish between drift velocity and mobility. State microscopic form of Ohm's law. State macroscopic form of Ohm's law. What are ohmic and non-ohmic regions? Define electrical resistivity. This question comes under short answers. Long answer. Describe the microscopic model of current and obtain the general form of Ohm's law. Obtain the macroscopic form of Ohm's law from its microscopic form and discuss its limitation. Explain the equivalent resistance of a series and parallel resistor network. So 6 short answers and 3 long answers you have to complete. Learn well, friends.